Good morning. Today, we are going to introduce the algorithm for finding shortest path. In the previous lecture, we studied the minimum spanning tree. So let's review the minimum spanning tree. And let's go to section 29.4, minimum spanning tree. All right. So what is a spanning tree? A spanning tree is a subgraph of the entire graph. The subgraph consists all the vertices of the entire graph, and the subgraph is a tree. So that is a spanning tree. The minimum spanning tree is the tree, the spanning tree whose total weight is the minimum. So that's the minimum spanning tree. And minimum spanning tree has a lot of applications. So if you just Google minimum spanning tree applications, you're going to see a lot of applications for minimum spanning trees. All right, so here's the example for minimum spanning tree. So we have this graph, and so here, this is a spanning tree, but it's not the minimum. So now we know the next one here, this total weight is 42. So the next one here, the total weight is 38. And this is also a spanning tree, and this is actually the minimum. And the minimum spanning tree is not unique. So here's another example, and this is also a minimum spanning tree, and the total weight is 38. So our task is to develop an algorithm for minimum spanning tree, and then implement the algorithm in our weighted graph class. So the weighted graph, we have all the vertices and the edges, just like a normal graph, but we assign weights on the edges. So the weights, and so here you can think about a lot of meanings on the weights. So in the map example, we have the distance as the weights, and so in some other situations, you can assign the weights on anything that is meaningful for your application. So we're going to look at the algorithm, and this is the algorithm we're going to use. There's actually a couple of algorithms. If you just to Google minimum spanning tree algorithms, and you're going to see a couple of minimum spanning tree algorithms. So the one, and we look at it, and here is the Prim's algorithm. So the Prim's algorithm. And the Prim's algorithm is this. The intuition is, so you have this, you're going to have minimum spanning tree. Initially, the minimum spanning tree, this is T, is empty. So you're going to keep adding the vertices into T from the graph. So eventually, so every vertex is in T. So this is the, you're going to form a minimum spanning tree. And so how are you going to add all the vertices? So this is how we're going to add it. Initially, we're going to add the starting vertex, S, and then we're going to keep adding the vertex, how we choose the vertex, for example, here. So these are all the vertices already in T. So these are not in T yet. So we're going to look for the edge with the minimum weight between the two sets. So the set is already in T, and the set is not in T. So this X, Y, this edge is the minimum weight among all these connecting edges. So we find this minimum one, we bring Y into T. So that's the intuition. So that we keep doing this, And eventually, we're going to bring everybody from the general graph into this T. All right, so this is the idea. And we're going to describe it and writing the pseudocode algorithm. So here is the pseudocode algorithm. And this is the one, it's minimum spanning tree. And so here is, we're going to get minimum spanning tree and starting from any vertex S. So eventually this is the minimum spanning tree, it's a tree. So the tree has a root, and so each vertex except the root has a parent. So that is here minimal spanning tree. And also plus we need additional information is we're going to have a total weight as a property in the minimum spanning tree. So we're going to describe it using pseudocode. So we have this T, let T be a set for the vertices in the spanning tree. So this is the line here, okay? Look at this line here. All right, initially add the starting vertex S into T. So we're going to add this into T. All right, now we're going to keep doing this. It's a while loop. While the size of T is less than N, N is the total number of vertices in the original graph. We're going to find X in T and Y not in T. So with the smallest weight on this HXY. So here's a diagram here. We're going to find this XY. So we find this is with the smallest weight among all these possible edges between T and V minus T. Add V, add W, I'm sorry, add Y. So here's add Y into T, add this Y into T. I'm going to set the parent of Y to X. So this is right here. All right, so this is the algorithm, and now we're going to refine it. We're going to do more work. And how are you going to do this? How do you do this? Find this XY. All right, so the way we're going to refine it is right here. We're going to introduce additional data structure here. So we just make it more close to the implementation. So we're going to add this data structure here. It's the cost. So what is the cost? So cost for each vertex. So this is the cost determines whether we're going to bring this vertex into T. So that's the cost that determines which one we're going to bring it into T. So we're going to have this cost initially, we're going to have cost of S is 0. So that's 0, 0. This is going to be 0. This is going to be the first one we're going to bring into T. So right. So here we're going to refine it. So you're going to see that we have a cost here. We're going to have a set this cost for S. So this is the starting vertex is 0, and all the other vertices, the cost is now infinite. So infinite. It's infinity. Big number. All right, so now Y, the size of T is less than N. We're going to find U not in T with smallest cost this. So we just find this. This is U is not in T now. It's in V minus T. So find the one that's going to be very easy to find it. Just look at the array and pick the smallest one. And that is one, it's the U, the cost of U. So this is the smallest. U is now going to add it into T. All right, so now you need to do adjustment. It's for each V not in T. So if there's H from U to V, so we need to look at the cost of V, see if this V, the cost is going to be changed as the result of adding U to T. So if it's changed, we're going to update the cost of V, this vertex, all the adjacent vertices to U. So this is right here. All right, so we have this algorithm now. You're going to see how close it is to the implementation. So let's do this now. I'm going to let's look at the implementation. So I'm going to close other tabs. Okay. Okay, so here we go. And let's do another one here is to open another tab. I'm going to duplicate this tab. Okay. All right, so here I'm going to look at the implementation. So this is the code. All right, so here's the code. Okay. Okay. So this is the code here. So let's just get the answer here. So I'm going to show you the code right away here. Quickly, now you can see this is the minimum spanning tree. All right, right here, the minimum spanning tree. The minimum spanning tree. The minimum spanning tree. It's right here. All right, the minimum spanning tree. Okay. All right. Let's do this. I'm going to have two windows. So this window, I'm going to have two windows here now. Let's do two windows side by side. Okay, I'm going to open another one here. Side by side. So this one here, it's the one. Okay, so let's do it this way. All right, I'm gonna do it this way here. I think I need to share the entire screen. All right, let's do that now. Okay. All right, I'm gonna go back to reshare this screen now. And I'm gonna have a new entire screen. Okay, you see my entire screen now? You see the both the algorithm and the implementation? Do you see both?
Yes, sir.
Okay.
Yes.
All right, so let's compare now. We're going to implement this algorithm. So this is here. Okay. Now you've been through in this many classes and in many practice on this programming. So from your 1301, 1302, and other classes, now coming to this class, this is all the skills and accumulated your ability and to write a code. And so now in this class, we're going to look really more advanced coding techniques. You're going to see here, you have to design the algorithm and you have intuition. So a lot of problems you have early on when you start writing programs, this is really simple thing. So now we have, you need to have the algorithm to think about how to solve the problem. Okay, and describe the algorithm using pseudocode and refine the pseudocode and make it very close to implementation and write in the code. All right, so here, this one here, minimal spanning tree. So look, we have this two methods, get minimum spanning tree. So this one with no arguments. All right, so this one doesn't matter, you just get any minimum spanning tree. All right, look, this is actually here, it's get minimum spanning tree starting from index 0, whatever that index is 0 in the graph, that's the one is going to be the starting one. All right, so here it is the second get minimum spanning tree with a specified starting vertex. So that's the one here we have with specified starting vertex S. All right, so now we have the cost. So we get this cost here, and this is the array. every vertex is associated with a cost. So this the size of the array, it's the number of vertices. And we're going to assign it, everyone we're going to assign the infinity. So this is the infinity in the Java language. Other languages, you can also get the infinity. Just do a Google, see what is the infinity in C++, in Python, in JavaScript. You can get all this. Java has this double in the class. If you have double value, double dot, and this is the positive infinity defined. Other languages, you don't have it. You just choose the minimum, the maximum value. That is the infinity, positive infinity. All right, so here, the starting vertex, its cost is 0. So that's right here, 0. So here, we have now all this here, the cost. And so we need to know, when we have a tree, we need to know the parents for each one. All right, so the root, the parents of the root is denoted as -1. So that's a special notation, means it's a root. And the total weight is initially 0. So here. All right, so now we also need to have record the sequence of this finding all this vertices bring it into the minimum spanning tree. So starting from S, the starting vertex, and who's the next one? And who's the next one after this next one? So that's the sequence. We're going to put it, we choose the data structure, we're going to choose the array list. So see how you're going to choose the right data structure? You don't choose a set, because if you have set, there is no sequence. You lose the sequence. All right, here we need to have this list. You can maintain the sequence. All right, so we can choose this data structure list for this purpose. Now, eventually you're going to see this is we're going to return MST. It's minimum spanning tree. So you're going to have this return. You're creating this object, a minimum spanning tree. The minimum spanning tree has starting vertex, parent, T, and total weight. See, this is this minimum spanning tree right here, minimum spanning tree. All right, so now this is the while loop. Why? The size of T. So T dot size. So what is T? T is the list. List has this method. It's the size. All right, here is the less than get size. So here's this dot get size is the number of vertices in the graph. All right, we're going to find this U. Okay, so now how you find a U? Let's make a U. It's initially is -1, is we don't find it. Now see how we're going to update this U right here. So here for this I is so from 0 and I is less than or equal to get size. And so for every vertex, we're going to see if it's not in T and it's the cost is the smallest. We're going to find the current cost. This is the current cost is infinity. And now we're going to update the current cost. Whichever is the smaller one, we're going to update it, becoming the current minimum cost. And so that one I is now assigned to U. After this for loop, we have this U. This is line 7 in the algorithm. We find it. This is how you see. This is a lot of details. You first have to have this all the steps right. You have this right algorithm, and you be able to describe it, and you be able now to write the code. So all this, you need to do all this, train yourself to practice how to do all this. And this is all training, and eventually, and you'll be able to do all this on your own, writing all your code, and get a job. And so your job will require you do all those things. Okay. All right, so now we're going to add this U to T. So here is, hey, we just want to make sure the graph is connected. So there's sometimes if you end up with the graph is not connected, you're not going to bring everybody into this T. So this is the defensive programming. So we have this U. If U is, so here, U, right here. This one here, U, if U is equal to -1 means you didn't find it. So you're gonna just break it. All right, so it's over. You didn't find it, and so we're gonna to break out of the while loop here, okay? And so if you find it, add it into T. So this is add U to T here in the algorithm. All right, so now we add something into T so that we bring a new weight into the spanning tree. So this is the cost of U. It's added into the weight, total weight. All right, so now we need to do this part, the adjustment. So for each neighbor of U, so we're gonna see if this adjacent vertex, if it's not in T. All right, so here the cost of E dot V, so this is the other end of this vertex. So this is E dot U and E dot V. So this is E dot V. If it's greater than, if this is current one is greater than this new age, this weight. So we're gonna update the cost of E dot V and also update the parent. So this is the code. See, that's how we're gonna implement it. So see, you have this algorithm and now refine it and implement it. So this is all the implementation. All right, so now let's look at the shortest path. All right, so this is the minimum spanning tree, look, minimum spanning tree. Now the next one is shortest path. What is shortest path? Shortest path is this. The example, we're going to look at the shortest path. So, all right, let's look at this diagram. So here's a diagram. How do you find the shortest path? Let's say from this vertex 1 and 2, 4. Okay, so there are many passes. So this is the 1, 3, 4. So what is the shortest path weight? It's 18. All right, so is this the best? Okay. All right, so I think it happens to be this one is there's another there's different passes. I think this is 18 is probably the best. Yeah. Just look at the diagram here. All right, what about this here? This one here, from 1 to 5. So from 1 to 5, okay, let's look at 1 to 5. It's 9, 7 is 16. So if you go 1, 6, 5. So this is, you're gonna weight is 9 and 7. That's 16. All right, so is this the shortest path? It is not, because there's another one, I see it. It's from 1 to 2. That's 5. And 2 to 0, it's 1 is 6, and then plus this 4 is 14. So this is actually shorter than the first try. All right, so you got the idea. So what do we need to do is the shortest path. The path, the total width on the path is the shortest amount or possible path. All right, so the algorithm we are going to present, it's by Dijkstra. It's called Dijkstra algorithm. Okay. So the algorithm we're going to present, it's right here. It's this by the Dutch computer scientist Dijkstra. So this is Dijkstra algorithm. So Dijk's algorithm can find the shortest path from any vertex. And actually, this algorithm in the process, it's going to find the shortest path from a single source vertex to all the other vertices. All right, so the idea is this. I'm going to first describe the idea is right here. And this is the idea. So you're going to have this, it's going to be it's a shortest path tree. So the result we're going to get, it's this the algorithm here. It's get the shortest path. All right, the get shortest path, and the result is the shortest path tree. It's a tree. All right, it's the shortest path tree. So for the minimum spanning tree, we get the minimum spanning tree. It's a tree. So the tree has the root and all the vertices except the root, and they all have the parents. So that information has to be in the tree. And for the minimum spanning tree, you have a total weight. All right, for the shortest path tree, we are going to have this is the root and all the vertices, and they have parents except the root, right? And so that's all I think we need for the shortest path tree. Shortest path. So this is the tree. So we're gonna have what we're gonna do is very similar to the minimum spanning tree. Is we're gonna have this set T. Initially, T is empty, and we're gonna bring S into the T, and then we're going to keep adding a vertex from V minus T into T. So how do we choose this one? U. So we're going to choose, so there's a lot of vertices now here in this V minus T. So which one we are going to choose? We're going to choose the one with the minimal cost. So look here, how do you define this minimal cost? So it's that is really the key. It's very similar to the previous algorithm. So this one here, the minimum cost is this. So all the vertices here, the minimum cost is this. The one here, the vertex. So please look at this vertex U, and this is the cost. It's the shortest distance to S. So this will be the cost. So this cost is relative to the source. So the distance to the source is the shortest to S. In the previous minimum spanning tree algorithm, so when you define the cost, it's just to any vertices in T, the cost, that's the minimum cost. So here the minimum cost is the distance to S. All right, so if we have identified this U now, so we're going to bring U into S, and now we're going to adjust the cost for this V1 and V2. All right, so this is the algorithm now. Let T be a set that contains the vertices whose paths to S are determined. Initially, T is empty. We're going to set cost of S to be 0. So that's just right. It's to itself. S to itself is cost is 0. And all the other cost is set to infinity. Okay. And now here, the while loop. Y cost of T is less than N. Find U not in T with the smallest cost U. Add U to T. For each V not in T, okay? And UV is in E. So it's there. V is not in T, but this is in E. So we're going to look at the cost of V. If the cost of V is greater than cost of U, so this is the U. U is already added into T. U cost of U plus and this is the h, u, v. So now we're going to update this cost of v to become cost of u plus w, u, v. And now we're going to set the parent of v to u. All right, so here, that's the key. I'm going to bring up the other algorithm. So let's just compare it and you're going to see the difference. So I'm going to bring another one here. It's let's do this here. I'm going to add another duplicate the tab. All right, so here I'm going to look at this the minimum spanning tree algorithm. Okay, so let's compare these two algorithms. Okay. So this is minimum spanning tree algorithm refined, and this is refined, all right, with the cost. Okay, so you're going to compare both. All right, so this is the shortest path, and this is the minimum spanning tree. So we're going to have this cost. Look, this is very similar, but the key is right here, this one here. You look at this here, the adjustment. So here, how are we going to adjust this, the cost? So this is for the minimum spanning tree for each u not in t, okay? And uv is in h. All right, if cost v is greater than this h, so the weight of this h, and now you're going to update to the smaller one. So this is assign the weight of this h into cost of v. All right, here, see the difference is this. If cost of v is greater than cost of u plus the h, the weight on this h, and now we're going to update this cost of v is, so what is the cost of u? Cost of u is already the distance from u to the source. So that's the distance from u to the source. All right, so very similar. I want you to look at this, the example. The example I'm going to give you, just look at the book here. This is the code. This is the example here. All right, you can play this example using the same example and apply shortest path and minimum spanning tree. See if you get the identical result. There's not the same. They're not the same. You're not going to get an identical result. Okay. So because the shortest path is different from minimum spanning tree. So let's look at this example here now. We're going to start with this vertex. This is the one. We're going to start this one. The source is one. Okay. All right. So what is the initial cost? This is cost of this one is 0. Okay. All the others are infinity. All right. So what's a parent of this one? It's a special notation. -1 means it's the root. Okay. This is the root. All right. So now this is the root right here. All right. All the others, the parents are not determined. All right. The next. So we're going to add this. T is initially is empty, right? So look at the loop here. So you're going to see this is, and the loop, the while loop. So, and the size of t is less than n, and find the u. So now, which one is your u now? You're going to find with the minimum cost. That is this one. So you're going to add 1 to t. All right. So now the next, add 1 to t. So when you add 1 to t, and you're going to adjust the cost. So 1 is added. So what is now the cost for 2, and the cost for 0, and cost for 6, and the cost for 3. So these are all adjacent to 1. So those are the costs are updated in this this algorithm right here. Okay, let's bring that algorithm side by side. So I'm going to have another, let's do this here. I'm going to bring this algorithm side by side so you can see this and compare this to, so here. Okay. All right, so here's the algorithm. And this is your diagram right here. Okay, this is your diagram. This is the algorithm. Okay, all right. Okay, now the while loop, the next iteration. So which one we're gonna find the smallest cost? So which one is the smallest cost? Okay. All right, which one is the smallest cost? Which one? Is this one. Okay. 5. So the vertex 2. So the next one you're going to bring it into this T is 2. So 2 is going to be bring it. So this is 2 right here, 2. All right, after 2. All right, so you add 2 now, you're going to adjust all the cost. So the cost is updated and the cost, this cost is updated. Okay. So the cost is updated. Now, after this, which one is smallest? Is now this one, 6. So you're going to bring 0 next time. And now adjust all the cost. All right. Please just spend a little time to look at this example and do both. For shortest path and for minimum spanning tree, you can use the same graph and do this and see what the result you're going to get. Okay. All right. So by doing this, you're going to understand both algorithms. Okay. All right. Any questions? Okay. All right, I think it's best for you to digest this material and to really appreciate the algorithm and appreciate the process and for developing this from algorithm, intuition, to pseudocode, to describe the algorithm, and then eventually to implement the algorithm. All right, any questions?
No, sir.
All right, well, thank you very much. I will see you next week. Goodbye.